talk about a paper that I wrote with Jordan Kotler recently on ER equals EPR in DS-CFT, and I'll mention a little bit at the end about how it might work out in celestial holography. So the basic idea of holography is that there are no bulk observables in quantum gravity, and we want to find some dual representation, the holographic principle, which has never been sort of clearly stated in a general context outside of ADS, is that some kind of quantum field theory without boundary would be dual to a bulk theory of quantum gravity. And roughly speaking, that quantum field theory would, of course, many modifications have been considered because we don't yet know how to think about this in the most general way, but would live at the boundary of the space-time. And one of the lessons that we've learned from studying, well, from a number of things, which I'll just mention, which we heard about in a beautiful talk by Hong this morning, is that the bulk space-time, understanding how the bulk space-time emerges, is intimately tied in with the structure of quantum entanglement of the degrees of freedom that live on the boundary. And that's the slogan, ER equals EPR. And probably the best understood example of this is what Hong was talking about this morning, is in the thermal field double in ADS-CFT, and I'll redraw his pictures here. And what we learned there is that, so we could take, so we have a CFT, these are both ADS regions here. We have a CFT2 and a CFT1 here. And nominally, one would think that this CFT1 would be dual to this region, and the CFT2 would be dual to this region. And there's some truth to that if we think about these regions being defined, expanding around the Bowler vacuum. So there's a Bowler vacuum for this ADS Schwarzschild, in which there are no correlations between points here and points there. It's kind of sick because it has singularities on the horizon. And so there's no correlations here, but there's, of course, the Hartle-Hawking vacuum, which is a global vacuum, and that's the more natural one. And in that one, there's correlations, hence between the scalar field here and the scalar field here, hence the EPR. That's what just explaining the slogan here. And so once you get the correlations here, you also get, so this is the EPR, and then this is the ER. Now, so that's probably the best understood example of ER equals EPR, but it's definitely not specific to anti-de Sitter space. And where I'm going here is I want to, expand this subject away from, wonderful work being done in anti-de Sitter space, but there are many other kinds of things that we want to understand. And one place where we do understand this is if we consider pair creation. Let me talk about a magnetic field. You have pair creation of magnetic monopole in a magnetic field. That's the Strominger process. And you can consider there are various theories, like, for example, just Einstein-Yang-Mills theory, in which there are solutions that look like a magnetic monopole. And there's a free parameter, which is the size. I think there are more examples of this, but I think it's something that was worked out by Eric Weinberg like 30 years ago or something. There's a size to the magnetic monopole. If it gets too small, it gets inside its Schwarzschild radius. This solution actually turns into a black hole. So if we consider pair creation of the magnetic monopoles, there's obviously no correlations between the scalar field here and here. And if you compute this, this can be computed with an instanton, and the instanton gives you the green function in this background. There's no correlations here. But the second you pass this threshold, there's two things that happen discontinuously. One is you find that you get an extra factor in the instanton proportional to the black hole entropy. So it's a discontinuous term. You change the topology, and that tells you the fact that it's e to the s black hole entropy, not e to the 2s black hole entropy. That 2 was very important. That tells you, it shows you how smart semi-classical gravity is. It tells you that this black hole is correlated with that black hole. So they're like an EPR pair. And at the same time, you find that the green function, if you have a scalar field here and a scalar field here, the green function that this gives you has divergences as this approaches this, a point on the horizon related to if these points get near each other going through the black hole. And the geometry also shows that you get an Einstein-Rosen bridge here. So again, this is an example of ER equals EPR, which we don't understand, which of course we can't analyze it in the same crazy detail that we can in anti-de Sitter space, but it shows that this phenomena of space-time emergence from quantum entanglement is very robust, or is more general than ADS. And of course, but I also want to add that there are more intricate, in a way, more beautiful emergence of space-time, which Dan and others pioneered, where you talk about, there's probably more than one Dan in this room, Dan Harlow, where you talk about space-time emergence from quantum entanglements of regions on the boundary. So this is obviously a very rich and beautiful subject. So what I'm going to talk about here is an example where not just a little wormhole arises, but where a whole space-time, namely de Sitter space, can be understood as arising from quantum entanglement. And I'm going to do it in the context of DS CFT. So, and it's going to turn out that, so DS CFT is very different from ADS CFT. ADS CFT has proceeded primarily from a sort of a top-down approach. We start from string theory, we understand everything in glorious detail, and we can do calculations and match both sides. We don't have any microscopic theory of de Sitter space, except for, well, there is one example, I guess, obviously, of gravity, and that does fit beautifully into this framework, but that's a slightly weird theory. And so we want to not hang on too tenaciously to ADS in trying to, we want to take some things generalize and some things don't. And what I'm going to say in this talk is that de Sitter space, if we're trying to think of going from ADS to DS, the structure of de Sitter space is much more like the structure of ADS Schwarzschild, that we can understand it much better in that way than trying to think of it somehow as a direct transcription of ADS in its zero temperature ground state. Now, the first thing about DS CFT, so you see that this picture is really like that picture. I just don't have the singularities there. And And so, but now it starts to get different because the boundaries of de Sitter space. So I'm going to talk about 4 dimensions. And so the boundaries of de Sitter space are 3 spheres. And so somehow the dual theory, which should be a conformal theory just by virtue of the fact that the isometry group, the simple fact that the isometry group of de Sitter space is SO4, 1, and that acts on like the conformal group on the 3 spheres at the boundary. So that's a kind of stupid, simple reasoning that we will borrow from anti-de Sitter space. But now something we can't borrow is that anti-de Sitter space has a crazy simple structure, which it didn't need to have, which is that the states in the boundary theory are exactly the same thing. The Hilbert space of the boundary CFT is completely the same as the Hilbert space of the bulk quantum theory of gravity. And there is no way that can happen here. The time in the boundary is the same as time in the bulk. And there's no way that that can happen in de Sitter space. Well, at least if you insist on the holographic dual living on the boundary. Some people would like to have it live on the horizon. That might work too, but that will be throwing away different things from ADS. And I'm choosing to keep the lesson from ADS that the dual should live at the boundary and see where that takes me. So if there's a conformal field theory in 3 dimensions, states on a conformal field theory. So where are the states here? So states in a conformal field theory have to live on a 2-sphere. And it should be a 2-sphere in the boundary. So we can take a 2-sphere up here, and that would be a place where you could have a state that lives in the conformal field theory. Now, the bulk states, this is an S2. I should probably use, I got colored chalk, so let me use red for, so this is an S2. And the bulk states, of course, live on S3s. Now, well, what is the state on that S2 dual to? Well, now I'm going to take another cue from ADS, is that the state should be, the state in the CFT should live on the boundary of the space-like slice on which the bulk state lives. So I can take a space-like slice in de Sitter space. There's space-like slices that end on this S2. And but what's different is that there are in fact 2 topologically distinct classes of space slices that live on any whose boundaries are any given S2 embedded in the S3 in the scribe plus of de Sitter space. And indeed, if I take the union, let me call this this will be a 3-dimensional surface, B31, B32. If I take the union of B31 with B32, then that is a Cauchy slice for de Sitter space. Oops, union. I take the union, thank you. That is a Cauchy slice for de Sitter space, and I can define a bulk state on that union. And so this observation was made in some papers already more than 10 years ago. And so that suggests that the bulk Hilbert space is somehow the square of the Hilbert space for the three-dimensional CFT. And okay, so now we've got the bulk Hilbert space being the square of the bulk Hilbert space, the bulk Hilbert space being the square of the boundary Hilbert space, and you can probably guess what the rest of the talk is going to be. That that we can realize we cannot realize, say, the Hartle-Hawking Euclidean vacuum as a state in the boundary CFT, but it's a thermal field double state, entangled, highly entangled thermal field double state in the square of the Hilbert space, of the boundary Hilbert space. And now we see that the whole space-time is emerging from not just an Einstein-Rosen bridge. Of course, it'll work out that in some way that this Einstein-Rosen bridge between the two static. So each of these would be, let me call this the southern static patch. And this would be the northern static patch. There's the Einstein-Rosen bridge, which will emerge from the quantum entanglement. Now, there's another thing that I need to, any questions about that?
I'm a little confused about how the static patches relate to the slices that you drew.
For good reason.
Okay.
Yeah. for good reason. And we, yeah. Somehow we started out with a different way of generalizing. We thought that this, there's sort of a wormhole.
Yeah, that's the naive thing.
Right.
Yeah.
And we thought that somehow it was gonna be quantum entanglement between the past and the future. That was, you have to turn some things, but not everything on its side.
Yeah.
You have to multiply, you have to turn some things, but not everything on its side, and you have to multiply some things by I and other things not by I. But it's all, so we don't have the luxury of string theory to tell us where everything goes, but we do have self-consistency. And I don't think there is another self-consistent way. This is the bottom-up approach. I don't think there's another self-consistent way of thinking about this. Now, we sort of thought about this kind of thing. There was a paper with Jim Seng Ing, and there was a Japanese group, Hosoya and some people, and also Moldacina and Pimental, analyzing quantum entanglement between states living on slices like that. And somehow it just got complicated and never went anywhere. I didn't know what to do. And I don't know why we didn't think of it this way earlier, but the important point to kind of make this come out the way we want it to come out, it's really important to go into the quasi-normal mode basis. So what is a quasi-normal mode? So if we take the southern diamond, this will be drawing this picture many times. So we have a southern static patch and a northern static patch. And a quasi-normal mode is a mode which dies exponentially. It's defined with respect to a patch. It's one which dies exponentially as you go forward in time. So they go like e to the minus t, rather than oscillating. Okay, probably more familiar with them in black holes, where they have imaginary frequencies, and in fact they're hoping to observe the quasi-normal modes at LIGO and in the ring down. And but you can also have a quasi-normal mode for the northern patch. So the ones that decay exponentially will have singularities along here. But then there's also quasi-normal modes for the northern patch, which have singularities along there. And these things actually form a complete basis for de Sitter space. And this was shown in a paper by Jafferis, Lipsaska, Ing and I about 10 years ago. And we just showed in a very pedestrian way that you take the quasi-normal modes and you quasi-normal modes and anti-quasi-normal modes, and you sum them, and you get the complete basis. You can make the green function out of it. I'll refer you to that. Now, quasi-normal modes for black holes, which you've probably heard about before, are not complete in a black hole spacetime, but there is some sense in which they are complete in the region around the black hole. In other words, if you think of there are plane waves traveling 1 million miles away from the black hole that can't be expanded in a quasi-normal mode basis, but there's some sense, which nobody really understands, in which quasi-normal modes are perhaps all the intrinsic, are a complete basis for the intrinsic degrees of freedom of the black hole. Okay, so what is the quasi-normal mode basis? What do these things look like? Oh, but before we start to go into any details, they decay exponentially in time, and that it includes, this could be static patch time. And so the Hamiltonian that Hong was writing is not Hermitian in this basis, right? Has imaginary quasi-normals have imaginary frequencies. So it's not Hermitian in this basis. And so already we're seeing the weird eyes come in, but they are a complete basis. And so we could just proceed and see where it leads us. And I think it looks interesting where it does lead us. Okay, so let's use the metric for de Sitter space, which probably looks most familiar, minus dt squared plus cosh squared t d psi squared plus sine squared psi d theta squared plus sine squared theta d phi squared. Okay, this should look familiar to everybody, I hope. And now we're just going to do a free scalar field, box minus m squared phi equals 0. And let me just write them down so you can see them. The phi, there's two classes of quasi-normal modes labeled by plus or minus. Is equal to I e to the, this is just a normalization factor, H plus. H plus is the conformal weight under the conformal group SO41. It's equal to 3/2 plus or minus 9/4 minus m squared L squared. Okay, now I believe that the results that I'm going to describe are true for any value of m, including in the oscillatory regime. We haven't worked that out. We're going to work in the range where this thing is real. And moreover, we have to exclude the case where this thing is integers that also requires special treatment, because a number of the formulas that I'm going to write down are divergent in that region. So it's e to the minus pi h plus over sinh t minus cosh t cosine psi minus I epsilon sinh minus cosh minus I epsilon to the H plus or minus. And then there's also an anti-quasi-normal mode, which is the same thing, except this becomes a plus. Okay, so it has a singularity at the opposite side of the sphere.
That's what the boundary conditions are for the quasi-normal modes.
The boundary condition for quasi-normal modes in de Sitter are that, well, I mean, that in the static patch, they fall off exponentially in the future.
So we have one set of modes for the north and one set.
Yes, yes. So the ones for the south are singular along this line, and the ones for the north are singular along that line. And we need both of those in order to have a complete basis. Otherwise, the Klein-Gordon norms would have to vanish because they're conserved. Otherwise, you could get into a very direct contradiction.
So, but Andy, except where they're singular, they're defined on the whole de Sitter, or they're defined only within the patch? Or
they're defined everywhere.
They're defined everywhere.
They're defined everywhere. Yeah. Well, I mean, and they're even defined where they're singular by the I epsilon description. And these earlier papers from 10 years ago contain a lot of discussion about asymptotics of these and all that kind of stuff. They do something. Interestingly, the plus modes fall off exponentially like H plus up here, but they have a delta function with a coefficient that falls off like H minus over there. Anyway, there's a lot of fun relationships with these, but okay. So now we have a killing vector. Let's call this killing vector L naught. I think Hong was calling it H right. So we have this killing vector L naught, and we can write it very explicitly, which is L naught is minus cosine psi dt plus tanh t sine psi d psi. But if we went to static patch coordinates, this would just be d by dt static in static patch time. Okay. Now we find it's easy to see that L naught phi plus or minus quasi-normal modes is equal to minus H plus or minus phi plus or minus quasi-normal, and a similar formula for without the minus sign for the anti-quasi-normal modes. And and these are also going to be highest weight states, which I'll explain in a second. But let me just say now that H static, remember, of course, is equal to what we would call the static patch Hamiltonian is I times L naught. It's I d by dt, right? So these L naughts have real eigenvalues. Okay, all right. So now there are, of course, 9 more generators, which we can write as spatial rotations JK. And then we have boosts, which I call M plus K and M minus K, depending on whether they raise or lower L naught. Okay, and I've already written out too many explicit expressions for Killing vectors, so I'm going to stop there. And so in addition to these things, importantly, M minus K, phi plus or minus quasi-normal modes is equal to 0. So they're annihilated by all the raising operators. And similarly, the northern modes are annihilated by all the lowering operators. But I'm using a specific definition of L1 here adapted to the southern patch. There'd be a minus sign. Obviously, there's a symmetry relating north and south. So I have a very nice set of modes, which is the kind of set of modes that a conformal field theorist would use in analyzing. This is how you would like operators in the boundary theory to transform. Okay, now another result from Jeffers et al. Well, okay, so let me introduce a multi-index B, which just is all possible descendants with m minus m plus k, so on. So far we have 4 sets of modes. The complex conjugates of these, which changes the I epsilon prescription. And then we have 5 plus or minus anti-quasi-normal modes and 5 plus or minus anti-quasi-normal modes. So, now, one thing that what was shown in Jeffers et al. Is that this is an overcomplete set. This is actually double what we need. And there are different ways of understanding this. One is that if you think of these as conformal primaries on the 3 spheres, you would already guess that they're somehow related by a shadow transform. You can also think of these are like Neumann and Dirichlet modes. You only need half of them. So we are simply going to erase the minus henceforth. And now we have 4 sets of modes.
Andy,
Yeah.
if we just ask for the highest weight condition to be satisfied, is that like a completely independent way of arriving at the same quasi-normal modes?
Yeah, that's probably how we found them. I can't remember, it was a long time ago, but yeah. And obviously that's what I don't know why we weren't thinking of it this way 10 years ago, but obviously if you want to make context between both de Sitter physics and the boundary CFD physics, you need to be at a basis that is a natural basis for the boundary CFD physics. Okay, but now I want to do these aren't the right modes for our purpose, and this is going to get to Dan's question. It turns out these modes are non-vanishing everywhere, typically non-vanishing everywhere in de Sitter space. And it's possible to construct, let me divide de Sitter space into 4 regions, which I'll call south, north, future, and past. And it's possible to define, so this is 4 sets of modes here. It's possible to define 4 different sets of modes, which have the property that they're, one set that's non-vanishing only in this region, another set that's non-vanishing only in this region, and then another set that's non-vanishing only in this region, and then another set which is non-vanishing only in this region. And for example, if I define phi b fn as an obvious notation, one that is non-vanishing in f and n, as phi b plus qn plus phi b plus qn star. And I chose my normalization of the quasi-normal mode, so it came out in this simple way without any phase factors. Then you find that those 2 modes go the different way around the branch cut. When you get down to here, they're just 0. This one vanishes in P and S. Okay, so we're going to use, and you can of course invert these relations, you have something like phi b plus qn is equal to 1 over 2 sine pi h plus e to the minus I pi h plus phi b fn plus phi b ps. And then there's 4 more sets of modes like this. And so these are like Rindler modes, quasi-normal. They're like Rindler modes, but with imaginary Rindler energy. And okay, now I wanted to find the standard Klein-Gordon inner product. Let me not write it out, but this is standard Klein-Gordon inner product on complete space-like slices. And now I can define operators phi hat b fs by taking the Klein-Gordon inner product of the scalar field, the bulk scalar field operator with the mode phi bps, obviously. Okay, and then I can compute commutators. And now notice that these things don't depend on x, right? These are just a tower of primary states and their descendants. So these things are identified, can be identified with operators in the dual conformal field theory that lives on the S3. And so, because they don't have any bulk X dependence. And in a moment, I'll write down a bulk reconstruction formula. So, yeah.
But are the dual to local operators on the boundary? Because they
Yeah.
don't seem to contain the information at the boundary point.
That's right. So, well,
Or maybe at the.
it's singular here. So it's dual to an operator located there. It's a quasi-normal. It obeys the conformal primary conditions for somebody at the North Pole. And I'm taking that operator and all its descendants, an operator insertion there and all its descendants, operator insertion here and all its descendants. And those are in one-to-one correspondence with the states you would expect. So the basic hypothesis of DSCFT is that there are one operator for every conformal primary wave function at a point on the sphere. But instead of thinking about points, different points on the sphere, I'm just doing conformal primaries at one point and then taking all the descendants, which is like differentiating their location. Because I want to talk about states, not correlation functions. Most of the previous discussion of DSC centered on correlation functions. Yeah.
Is there a sense in which you can do an asymptotic function with some coordinates and you have source embed out of this?
Yes, there is. I think you could probably make that precise in facility of gravity. The pluses and the minuses, H plus and H minus would be like source and value. I mean, I shouldn't say yes, there is. I should say yes, I think so.
Thank you.
Yes, I think you could do that, and it wouldn't be obviously, you could do it in a self-consistent way. Okay, so then we have commutators, psi b, psi hat b fs, phi hat b ps, a ps. So this is like a bulk commutator, not a boundary commutator. And that has an I in it, and it's NAB, and NAB is just, we normalize the two-point function of the primary, and then these are just computed with SO41 group theory. And that's also, if I get the same thing, if I exchange north and south, maybe with minus sign. And and in particular, as should be obvious, the north operators and the south operators commute with one another. And the south operators, or the south wave functions, are a complete basis for anything that goes on in the southern diamond. And the northern ones are for anything that goes on in the northern diamond. Okay, so then I can define a vacuum state, in fact, a pair of vacuum states. A pair of vacuum states. Let me just talk about one of them. But already we see emerging here that we have two sets of operators, which we can identify the northern and the southern, which we can identify with two sets of states in the dual conformal field theory, not one. So we can define a vacuum, which is side head B Fs0 equals 0, and also, and that's equal to psi hat B Fn acting, I'm going to call this 0F, 0F, and there's a similar one for pass. These two vacua are related to dual representations of the theory, but let me not get into that because I'm rapidly running out of time. Nastya hasn't started glaring at me yet. Okay, so now we have a bulk reconstruction formula, which I'd also like to write down, which is simply, so we can, if we think of these guys as operators in the two-dimensional field theory, we have phi hat of x. The bulk field operator is just equal to minus I NAB phi A. I should raise this, NAB phi A PS of x phi hat FSB plus three more terms. So this is a bulk wave function. So this is a formula for the bulk field operator in terms of operators that act on not one copy of the dual CFT, but you need two copies because we have the southern ones and the northern ones. And so now finally, we have this formula, for example, the plus quasi-normal modes, and we can, the Euclidean vacuum is defined, these all have the minus I epsilon. Regional mode. So in the formula, zero U is equal to E to the I H. Phi hat PS A phi hat PN B. This is all in the exponential acting on 0F. Okay, so that's obviously something which is it's a thermal field double. And it's obviously something, this is the L naught eigenvalue. And it's obviously something which is correlating the two CFT3 Hilbert spaces. And then, of course, we did our homework, and you can do the trace over the northern Hilbert space of 0E, 0E, and you get what you have to get if we didn't mess up, which we didn't. You just get e to the minus 2 pi, which is 1 over the de Sitter temperature times the Hamiltonian in the static patch, which is equal to e to the minus 2 pi I L naught. Okay, so it's an interesting expression. Now, one important thing here.
Which one is Hermitian? Is it L naught or H static? Or neither?
L naught is Hermitian in the spaces. So H static is Rindler energy. It's ID by dt. Okay, so now we have a density matrix for the static patch, which is written as an operator in the dual field theory. And this gives the solution of something that was really bothering me for years. I think I discussed this with other people. In DSCFT, what is the thing that is the entropy? What gives the de Sitter entropy? And I didn't know how to. It seemed like something that you should be able to get a formula for, even if you don't know what the CFT is. You should be able to get a formula for it, a formal formula for it. But now we have this density matrix for the static patch, and it's just, S is, as usual, minus trace rho log rho in the two-dimensional, in the dual CFT. But at a temperature, instead of 1 over 2 pi, 1 over 2 pi I, which is equivalent to saying that it's a partition function in which you identify in Lorentzian time rather than Euclidean time. And so finally, let me say that this all carries, we believe, but we haven't finished it yet, that again, the structure in celestial CFT, the structure is much more like in DSCFT than it is in ADS-CFT. The conformal field theory lives on celestial sphere, which is up here, and it can't be simply identified with the bulk Hilbert space. It contains all the information, but it's scrambled up and put back together in a different way. And again, we can think about correlation functions here, and there's, of course, this sphere becomes identified with this sphere under the antipodal identification, but there's a Hilbert space, 2 Hilbert spaces of CFT, one that you can think of as, again, it starts looking like Rindler physics. I mean, celestial holography, you work in boost eigenstates, and so it looks a lot like Rindler physics. And we're trying, we haven't got to the end of it yet, but we're trying to get a similar formula for in celestial holography for which shows how Minkowski space itself emerges from a thermal field double state in the dual celestial field theory. We can't identify, it's clear that we can't identify the Hilbert space of celestial conformal field theory with the bulk Hilbert space of states in Minkowski space, and this is what we think we need to do. And I think I'm right on the bell.
Any questions?
So for flat space, do you also have an imaginary temperature?
Well, okay, so yeah, in flat space, there are two bases which have been widely discussed. In de Sitter space, you could probably do this in de Sitter space, but in flat space, there are two bases which have been widely discussed. One is the unitary principal series, where the conformal weights are 1 plus I lambda. And that, of course, if you've been doing two-dimensional CFT your whole life, you get a little nervous when you see operators with imaginary conformal weights, but imaginary conformal weights are real Rindler energies. Right? It's if this boost weight is imaginary, that means it's a real Rindler age. So whether it's real or imaginary, so if you do it in that kind of basis, it might look like a real temperature, but there's also an integral basis, which several groups have shown that there's also a discrete integral basis for modes in Minkowski space. I think the twistor people have been using this for the last 30 years, or 40 years, our old twistor theory is, but sort of in our language of scattering theory and so on, there's an integral basis. And so again, whether or not there's an I in there depends on how you set it up.
Another.
So this is by the way, it might not be so funny to have an I in the temperature if your energies are imaginary. So
Can you do basic fluctuations? I get 2 copies of the stress test.
yeah. This will. Well, sorry. This is a problem we're working on now. So I excluded the case where the conformal weights were integers. And that is a especially interesting case because that's where Vasilyev gravity lands. And it's just a different problem. And so for the metric, you're gonna land on that. But I think there doesn't seem to be any reason that won't be possible. Yeah.
Would it make any sense to take the S2 and cut it up into regions and talk about the entropies of regions as opposed to the whole thing, which you've done here?
I think so. And I think things like that should be possible. And I think there has to be, I mean, one really interesting thing to try to do would be to, one thing that struck me in Huang's talk, or many talks, but I was thinking about it again this way, is in all this structure of entanglement and so on, actually nobody really uses any string theory. They just feel good because it could all be derived from string theory. So it's really coming from, it's secretly bottom up, right? You have some sort of conjecture about how things should work out, and you show that it's self-consistent. So I think that it would be really interesting to try to derive some kind of Takianagi formula for subregion entanglement for these states in de Sitter space. And indeed, Takianagi and his have been defining these pseudo entropies, and they have this formula e to the 2 pi I L naught also appears in their papers for their pseudo entropies, and it's clearly related. They have eyes floating around. Maybe their eyes cancel our eyes, whatever.
Hyper eye, yeah.
In the flat space thing, I mean, there, you know, Wei Song and friends have written down Ryutakanagi like formulas for entropies of parts of the celestial sphere, which involve these swing surfaces where you shoot in null geodesics and then look
Yeah,
and stuff
yeah,
like that. So I don't know if that's should be thought of in this setting. Or...
I think so. I think so. I mean, basically, nobody's thinking. I didn't even until this recent project. I forgot about the things I was thinking about 10 years ago. Yeah, I forgot about this thing that de Sitter space was a double, because this was before all the. Yeah.
Okay, well, we should probably move on to the next thing.